If a black hole has no surface, why does its edge behave like one? I like questions that arrive like that. Simple, disarming, and then as you turn them over, astonishingly deep. Tonight I want to linger with that edge, the horizon, the not quite surface of a black hole. And I want to ask what it is made of, not of atoms or molecules, but of properties, of fields, of information, of memory. Because in the year 2024, the Event Horizon Telescope gave us a new polarized glimpse of the black hole at the center of our galaxy, Sagittarius A star, and in that light we saw order at the brink, magnetic fields threaded and spiraled as if some hidden fabric were shaping the flow of space's faintest embers. It is a view that invites us to treat the horizon like a membrane, a place where the universe keeps its accounts. Let me set the scene. Sagittarius A star sits about 26,000 light-years away, a giant of roughly 4 million suns worth of mass, cloaked in gas so hot it glows in radio light. When we look at that glow through polarized lenses, when we ask not only how bright the light is but how it is twisted, we can infer the structure of the magnetic fields near the boundary. The Event Horizon Telescope polarization image revealed those fields to be strong and organized, spiraling around the dark silhouette. That pattern echoes what we saw earlier in the black hole in the galaxy Messier 87. This similarity is a clue. It suggests that organized magnetic fields at the brink are not an accident of one object, but a common feature of black holes, guiding how they feed and how they fling matter back into the galaxy. What sort of edge can choreograph a dance like that? In general relativity, the horizon is not a material surface. It's a null boundary, a place in space-time where light itself turns inward. And yet, for a distant observer, for anyone who cannot reach inside the horizon, behaves as if it were a surface with physical properties. This is the heart of the old and beautiful membrane paradigm. Treat the horizon as a thin, stretched film, with electrical conductivity, with viscosity, with temperature. Let it respond to fields and flows, and you recover the correct physics seen from outside. It is a way of thinking that turns a mathematical boundary into a kind of physical skin, and it remains a powerful language for describing the near-horizon world. If that sounds like sleight of hand, consider what we learned when we took black holes seriously as thermodynamic objects. They have an entropy astonishingly proportional not to volume but to area. The larger the surface area of the horizon, the greater the number of microscopic states the black hole might be hiding from us. That area law led, in time, to the holographic principle. The idea that the information content of a region can scale with its boundary, and that a faithful description of the interior might be encoded on the edge. The horizon becomes a ledger, an account-keeping surface. That is a strange sentence to say about a thing which is formally empty, and yet it is the sentence our equations invite. And so we return to the ring that remembers. If the horizon stores information, then the black hole does not forget what falls in. It reorganizes that information in a way we do not yet fully understand. Some years ago, Stephen Hawking, Malcolm Perry, and Andrew Strominger proposed that black holes carry soft hair, delicate, zero-energy imprints associated with deep symmetries of space-time and electromagnetism. In that picture, the horizon is not bald. It can carry charges and memories that, in principle, influence what leaks back out as the black hole evaporates. Memory at the edge. Not a tale told by matter within, but an imprint on the boundary itself. The Event Horizon Telescope's polarized view sharpens this intuition. Polarization tells us about order, random, turbulent. Fields scramble polarization, coherent fields preserve it. To find coherence in the light from so close to the brink is to find a hand that steadies the flow. It suggests that magnetic tension and pressure, threaded through plasma, are shaping how material spirals in, and, perhaps, how some of it is redirected and accelerated away. Even where we do not yet see a clear jet from Sagittarius A star, the fields whisper that the ingredients are present and that the horizon is part of the machinery, not merely a passive boundary. This is a gentle, wondrous inversion. The surface that is not a surface takes on the responsibilities of one. It heats and radiates, it carries entropy, it resists and conducts, it stores and releases information. In the language of the membrane, it even has a kind of sheer viscosity and a finite electrical resistivity, numbers one can write down and use to predict how fields will thread and twist as matter falls. When we speak that language, we are speaking about the experience of the outside world, because that is all we can measure. The inside remains hidden by design. The horizon is a curtain that never lifts. And yet the curtain is not blank, it is textured with physics. So when you hear the simple claim that a black hole has no surface, remember the nuance. It has an edge that behaves like one for every purpose available to us. It is where the universe balances the books, where area keeps track of entropy, where soft hair keeps track of symmetries, where magnetic order shapes the river of falling light. The ring remembers, not in English or mathematics, but in the conserved quantities and patterned fields that leave their trace on the radiation we can see. And perhaps that is why the new polarized images feel so quietly revolutionary. They show us a memory made visible, a script written in light on the last circle around a darkness we can never enter. I have been thinking about what it means to endow an edge with traits. If you and I stand far away from a black hole and ask only what we can measure, the not surface grows a personality. In the old membrane picture, you replace the horizon with a paper-thin, time-like skin, a stretched horizon hovering just outside the true boundary. You then give that skin the properties an engineer would expect: an electrical resistivity, a thermal response, a viscosity. Astonishingly, the numbers are not arbitrary. The horizon behaves like an ohmic sheet, whose surface resistivity equals the impedance of empty space, roughly 377 ohms. Currents flow on that skin. Ohm's law holds. Fields thread and slip, as if across a conductor. A fiction that makes correct predictions is not merely a story, it is a tool for seeing. Once you admit that language, a great deal falls into place. Let a charged particle approach such a surface, and the membrane polarizes. Let a magnetic loop sweep past, and eddy currents appear. Let plasma try to shear around the hole, and the film resists with immeasurable viscosity. You can even treat energy extraction from a spinning black hole as a kind of cosmic electrical circuit. Match the impedance of the horizon to that of the distant universe, and you maximize power, precisely the lesson of the Blandford-Znajek mechanism that feeds relativistic jets. The mathematics says that both the faraway membrane at infinity and the stretched horizon behave as if they share the same surface resistivity, again that magical 377 ohms. The edge becomes a component in an astrophysical machine. So when the Event Horizon Telescope collaboration revealed, in the year 2024, that the light around Sagittarius A star is polarized in an organized spiral, it felt like a quiet confirmation of this picture. Ordered polarization means ordered magnetic fields. Ordered fields mean the plasma is not purely turbulent but guided, shaped by tension and pressure along coherent lines. The image does not show a literal wire, but the mathematics of a conducting viscous membrane predicts just such guided flows. The similarity to the Messier 87 black hole hints that this is a common script. Horizons and fields co-author the choreography by which matter falls, stalls, and sometimes escapes as collimated beams. There is another way the edge acts like a surface, and it lives in the language of thermodynamics. A black hole has an entropy proportional to its area, not its volume. That sentence sounds innocent until you realize that it implies an accounting system on the boundary. The larger the area, the more ways the black hole could be arranged microscopically without changing what we see from outside. It was a radical, now foundational idea that began with Jacob Bekenstein and was completed by Stephen Hawking's discovery that black holes radiate. The upshot is stark. The horizon is where you keep the books, because the number of hidden states is written on the area of the edge. Follow that line a little farther, and you arrive at holography. The suggestion that the deepest description of a region might be encoded on a lower dimensional boundary, that the world's informational budget scales with surfaces. Raphael Bousseau's covariant entropy bound and Leonard Susskind's formulation gave this intuition precision. In our context, the message is simple and evocative. If the interior can be faithfully represented by degrees of freedom living on the horizon, then the ring is not an empty outline. It is populated by the variables that remember. In recent years, the word memory has taken on a more literal character. Stephen Hawking, Malcolm Perry, and Andrew Strominger argued that black holes can carry soft hair, delicate, zero-energy imprints tied to deep symmetries of space-time and electromagnetism. These soft degrees of freedom live on or near the horizon. They do not carry energy in the usual sense, but they carry identity. Two black holes with the same mass, spin, and charge can still differ by their soft hair, and those differences can, in principle, influence what emerges in the long, slow leak of Hawking radiation. The edge once again holds the distinguishing marks. Even gravity's own voice tells us that the edge has character. When two black holes collide and settle, the merged object rings like a struck bell, emitting gravitational waves at discrete damp tones called quasi-normal modes. Those tones depend only on the mass and spin of the final hole. A clean signature predicted by general relativity and first heard on Earth by the Laser Interferometer Gravitational Wave Observatory in the year 2015. That ringdown is an edge phenomenon in the most direct sense. Perturb the horizon, and space-time responds with a spectrum that encodes its global properties. A surface that rings is a surface with identity. And yet, there is a subtle counterpoint. Ask how a black hole deforms under an external tidal field, how squishy the edge is. And the answer, in classical general relativity, for a non-spinning hole is not at all. The tidal love numbers, which measure that deformability, vanish. A neutron star bulges, a Schwarzschild black hole does not. The edge, in the purely classical theory, remembers in its thermodynamics and radiance, but it refuses to carry a tidal imprint. That stark contrast reminds us that what we call an edge is a composite idea. Some properties are real responses of geometry. Others are the effective behavior of the membrane we use to describe what distant observers can see. Now return to the polarized light near Sagittarius A star. Coherent magnetic fields, so close to the brink, suggest a particular mode of power. Rotational energy from the hole can be tapped by those fields and carried away, in principle, as jets. Whether our own galactic black hole launches a bright jet is an observational question still open to the skies, but the ingredients, the ordered threading, the impedance matching logic, the membrane's ohmic currents are present. In numerical experiments and in elegant arguments, efficiency peaks when the field lines feel the horizon and the distant universe as matching loads, and that is precisely the intuition the membrane paradigm makes vivid. The edge is the terminal that closes the circuit. All of this sits atop a deeper, wonderfully modern development. The last few years have seen remarkable progress on the information problem, showing how to compute the fine-grained entropy of Hawking radiation in a way that recovers the expected page curve. The technical tools carry unfamiliar names, quantum extremal surfaces, entanglement islands, but the story they tell resonates with our theme: boundaries matter. Under the island rule, the true entanglement surface that counts the radiation's entropy can lurk near the horizon, effectively pulling part of the near-edge region into the description of what has flown away. It is as if the ring expands and contracts in the bookkeeping of quantum information, ensuring that the world remains unitary even as black holes evaporate. There is even a literal sense in which edge modes count. In gauge theories like electromagnetism, careful calculations of entanglement reveal additional degrees of freedom living on the boundary modes fixed by the normal electric field that restore consistency to the entropy and contribute precisely the terms that once puzzled everyone. Though this is not yet the full quantum theory of horizons, it is a tantalizing rhyme. The mathematics keeps finding information perched on surfaces. The universe, it seems, likes to place its memories at the edge. If a black hole has no ordinary surface, why does its edge behave like one? Because for us observers, forever outside the horizon is where dynamics, thermodynamics, and information meet. It is a conductor for fields, a ledger for entropy, a bell that rings with its own tones, a boundary that hosts the delicate modes of gauge symmetry, and a partner to magnetic order that shapes the fate of falling light. The Event Horizon Telescope's polarized images give us a new, empirical handle on that story. They show us not merely darkness surrounded by glow, but structure threads pulled taut by an unseen hand at a knot surface that behaves in every way available to us, like the most consequential surface in the cosmos. I keep returning to the feeling that the edge behaves like a fluid, not water in a glass, but a perfectly thin film whose responses can be written down as transport coefficients, conductivity, viscosity, heat capacity. In the membrane language, the stretched horizon is endowed with a surface resistivity equal to the impedance of empty space, about 377 ohms, and with a shear viscosity and other familiar fluid quantities. It is a poetic trick that turns a mathematical boundary into a material-like sheet. And yet it makes reliable predictions. Currents flow on the skin, fields couple to it, and energy is dissipated just as in an ordinary conductor with that particular resistance. Once you accept the horizon as a fluid, an entire bridge opens to modern physics. In holography and the fluid gravity correspondence, large black holes map to strongly coupled fluids whose shear viscosity divided by entropy density takes a universal value of roughly 1/4 pi in appropriate units. That tiny ratio, close to the quantum limit, says the horizon's effective fluid is extraordinarily slippery, resisting shear only weakly, while still carrying a great deal of disorder. You do not need the equations to feel the idea. The edge is hot, thin, and astonishingly efficient at moving momentum around. The mathematics behind this correspondence has matured over the last decade and more. It is one of the most beautiful ways we have of translating between curved space-time and ordinary fluid motion. This picture is not mere aesthetics. It touches the newest data. The Event Horizon Telescope's polarized view of Sagittarius A star, released in the year 2024, revealed a ring whose polarization angles are not random, but organized threads of magnetism coherently wrapped around the silhouette. When you interpret those swirls with general relativistic magnetohydrodynamic simulations, a particular state of accretion rises to the top, the magnetically arrested disk. In that state, magnetic pressure becomes so strong near the hole that it bottlenecks the inflow, piles up at the brink, and helps organize the plasma into ordered spiraling lanes. In fact, the collaborations modeling singled out a magnetically arrested disk with a rapidly spinning hole as the best bet configuration, once you account for how Faraday rotation either scrambles or, if removed by derotation, clarifies the pattern. The edge looks, in every sense, like a magnetized membrane that shapes the flow. There is an almost electrical elegance to how energy may be drawn from a spinning black hole in such conditions. In the Blandford-Znajek story, magnetic field lines that touch the horizon act like wires in a circuit. Maximum power is delivered when the load presented by the distant universe matches the internal resistance of the horizon. The membrane view makes this literal. Both the faraway membrane and the stretched horizon carry the same surface resistivity again, that characteristic 377 ohms, and the system behaves like an impedance-matched generator. Where the match is good, energy flows cleanly from rotation into Poynting flux, the electromagnetic energy that can collimate into jets. The edge is not only a surface, it is a terminal. Listen closely and the horizon sounds like a fluid too. Disturb it and space-time rings down in. Discrete, damped tones that we call quasi-normal modes, notes that depend only on mass and spin. In the membrane picture, those notes are the natural oscillations of a viscoelastic sheet relaxing to equilibrium. In the holographic picture, they are the poles of a retarded Green's function in a strongly coupled fluid. In either language, the song is the same. The edge supports collective motions, and those motions carry information about the whole object. It is a rare pleasure in physics to watch mathematics rhyme across such different descriptions. There is a deeper symmetry whispering at the brink as well. If you zoom in to the very near horizon region, the geometry acquires an ultra-relativistic character. The effective speed of light along the edge tends to zero, and the natural symmetry becomes Carolean rather than Galilean or Lorentzian. In that language, the standard equations that govern expansion and shear at a null surface read like conservation laws of a peculiar boundary fluid, a Corellian fluid living on the horizon. It is technical, yes, but the picture it leaves is simple, and evocative horizons behave as if a special, edge-bound fluid carries their stresses, charges, and flows. Even the counting of information seems to prefer edges. In gauge theories such as electromagnetism, precise calculations of entanglement reveal that additional would-be pure gauge degrees of freedom live on the boundary and must be included to get the entropy right. These are the edge modes, subtle classical configurations set by the electric field piercing the surface. Their presence fixes a long-standing mismatch and teaches a general lesson that echoes through quantum gravity boundaries host bookkeeping variables. When we translate that lesson to horizons, it becomes hard not to imagine the ring as an information register. Nature, for her part, is kinder than we deserve and offers laboratory metaphors, insonic analogues of black holes flows, where sound cannot escape. Researchers have observed the analogue of Hawking radiation in Bose, Einstein condensates, spontaneous thermal phonons created in entangled pairs across a sonic horizon. The analogy is not identity, and careful people argue over how much of the true gravitational story one can borrow. But as a demonstration that a horizon, even an artificial one, radiates thermally because of its edge structure, it is profoundly suggestive. A boundary with the right kinematics behaves like a surface with a temperature. That too is a way an edge acquires substance. Put these strands together, membranes with definite transport properties, holographic fluids with nearly minimal viscosity, polarized rings that prefer magnetically arrested disks, circuits that extract spin by impedance matching, boundary symmetries that read as fluid conservation laws, edge modes that restore entropy's logic, and even laboratory horizons that hiss with thermal quanta, and a single image emerges. The ring that remembers is not built of atoms, but of responses, not of molecules, but of constraints, not of stuff, but of symmetries and flows. Its substance is the set of rules that all observers outside must use, and those rules make the edge behave uncannily like a surface hot, conducting, viscous, and organized. The Event Horizon Telescope's latest polarized view simply lets us watch that organization in action. The horizon is where the cosmos writes in ink we can see. Shall we go closer still? In the next breath, I want to follow a single magnetic field line as it threads the brink, feel how it anchors in the membrane, and watch how information about that line, its twist, its tension becomes part of the ledger the ring keeps. I promised we would follow a single magnetic field line, so let us do that now slowly, carefully like tracing a strand of silk that has been thrown across a storm. Imagine the plasma around a rotating black hole as a luminous fog, threaded by invisible wires. Choose one wire. Far from the hole, it drifts lazily in the glow. Closer in, gravity tightens its curve. Closer still, space-time itself begins to turn, and the wire is caught in the whirl. There is a region outside a rotating black hole where space is dragged around like water caught by a paddle. If you were to hover there, you would be compelled to turn with the hole. Our chosen magnetic strand is pulled into that compulsory dance. Tension builds along it, like the twist in a rubber band between your fingers. In a conductor, that twist would launch a signal, a little shiver of stress racing along the band. In the plasma, that signal is a magnetic ripple, an Alphen wave, a magnetized pulse that carries information about the twist outward. You can hear, in the mathematics, a music of pushes and pulls. Where the field is strong and the plasma is light, the ripple runs fast. Where the field slackens or the gas thickens, the ripple slows and piles up. Now ask what anchors the inner end of that strand. In the membrane picture, it ties to the stretched horizon, the paper-thin surrogate surface we place just outside the true boundary. Give that skin its peculiar properties, and it behaves like a resistive conductor with a particular surface resistance set by the vacuum itself. When the twisted strand meets the skin, a surface current flows. That current does two things at once. It dissipates a little energy as heat in the fictitious film, and it exerts a torque, a braking twist, on the rotating space-time beneath. In that exchange, a fraction of the hole's rotational energy is handed to the field and carried away as electromagnetic power. Pointing flux, the flow of energy in a magnetic wind. Follow the strand outward, and you will see how the twist organizes the fog. A magnetic field resents being tangled. It pushes back with tension along its lines and pressure across them. That combination carves channels in the plasma spiraling lanes, where matter can slide inward and occasionally be redirected outward in tight, collimated funnels. We give names to these arrangements, but the picture is simple. The field lines act like guide rails, the plasma like beads that slide along them, and the horizon's effective surface acts like a terminal that closes the circuit. Where the match between the inner terminal and the outer loads is good, power flows cleanly, the rails stay taut, and the system finds a quiet, organized state that shines with polarized grace. What then does it mean for the ring to remember our strand? Not memory in ink, but memory in pattern. The surface current induced at the stretched horizon is not arbitrary. It depends on the orientation and twist of the field line. Change the line, and you change the ledger written on the skin. If you drop in a charged particle along that line, the boundary responds with a redistribution of surface charge, an electrical rearrangement that enforces the great accounting rules of nature. Those rules say that flux is conserved, that field lines do not simply end, that what goes in must be balanced by what is carried across the boundary. The edge keeps the books by hosting the charges and currents required to make the equations true. That is a very sober way of saying, the ring remembers where the strands have been. This is not an occult claim. It is measurable in the light. Polarization is a compass for the near-horizon world. The electric field of the radiation vibrates in a preferred direction when it has been sculpted by coherent magnetism. Trace that preferred direction around the ring and you reconstruct a map of order. Where the map winds smoothly, the field is well organized. Where it breaks or rotates rapidly, turbulent plasma and Faraday rotation, twisting of polarization by magnetized gas, have muddled the signal. Remove the muddle with careful modeling, and the underlying structure emerges, a spiral of preferred angles that mirrors the spiral of our imagined strand. Let us linger with the dynamics for a moment more. The horizon's effective skin does not merely carry currents, it resists shear like a viscous film. Disturb it, and it relaxes with a characteristic damping, the same way a drumhead yields and then stills. In the full geometry of a black hole, this relaxation appears as quasi-normal ringing, the discrete damp tones that announce the settling of the space-time after a disturbance. Translate the language across the membrane bridge, and those tones become the collective oscillations of an ultra-thin, hot conducting sheet. The equivalence is not an accident. It is a sign that the substance of the edge is encoded in its responses. A surface is what it does. There is a stranger, quieter layer of memory at work as well. In any theory with gauge symmetry, electromagnetism is the familiar example boundaries host additional, delicate degrees of freedom that record how fields cross them. They are not energetic excitations, so much as settings on a dial that must be specified to make sense of the whole. On an ordinary table, that distinction feels academic. On a horizon, it feels urgent. Those edge settings are the difference between one history and another, between one arrangement of faraway charges and the next. Two black holes with the same mass, spin, and overall charge can, in principle, carry different edge settings tied to deep symmetries. That is another way to say the ring can remember without storing matter in the usual sense. I find it helpful to translate all of this into an image from everyday life. Think of a lake at dusk with a thin sheet of ice forming on top. The water below is a volume, a depth we cannot see. The ice is a surface, a film that is not yet solid and yet has acquired properties you can test with the gentlest touch. Brush it with a reed and waves spread. Set down a dry leaf and currents beneath, push it along, scratch it, and the mark persists for a while, even if it is too faint to catch the eye. Now remove the atoms, remove the molecules, and keep only the rules that govern the reed, the leaf, and the scratch. That is the horizon. A film made of law. A surface that exists because the universe demands that observers outside obey certain relationships between what goes in and what comes out. Return, finally, to our single magnetic strand. It has wandered from the outer glow into the grip of the whole. It has felt the compulsory spin. It has launched ripples along itself, and it has pressed its information, its twist, its direction, its tension into the currents and charges of the membrane. If the strand were to slip beneath the true boundary, the ledger on the edge would change again to keep the accounting correct. The light escaping from just above would carry a faint whisper of these adjustments, a subtle coherence we can only just now begin to discern with our polarized eyes.
In the next step, I want to follow a photon born near that edge, one particle of light on a tight orbit around the darkness.
I want to feel the way space-time bends its path, how polarization is dragged, how time itself dilates and stretches the rhythm of its wave. And then, when that photon finally escapes to us after circling the brink, we will ask what story its orientation and phase can tell about the surface that is not a surface, the ring that remembers. I said we would follow a single photon, so let us release one now born in the inner glow, just above the brink, and let it skim the darkness. Its path is not a straight line, but a choreography written by geometry. Around a non-spinning black hole, there is a special radius, 3 times the gravitational radius, or 1.5 times the Schwarzschild radius, where light can, in principle, orbit on an unstable circular track. Near a spinning black hole, those special orbits split and shift with the spin, but the spirit of the story survives. There is a critical ring in the sky toward which near-grazing trajectories are funneled. That ring is what we call the photon ring, really a nested family of ever thinner subrings made by photons that loop once, twice, many times before escaping. It is not a material band. It is the bright edge of possibility, a pile-up of paths that the universe prefers. Our photon does not know this law. It only feels the pull. It slides inward, bends, and then, at the last moment, is captured by the critical curve, forced to arc around the hole before racing away toward us. With each extra loop, the path length grows, and the arrival time is delayed. The subrings become fainter and narrower, like echoes fading in a canyon of space-time. The beauty of this structure is not merely aesthetic. Those nested rings imprint universal signatures on interferometers, allowing, in principle, precise measurements of mass and spin and exquisitely sharp tests of general relativity. Even with sparse arrays like the Event Horizon Telescope, the geometry writes a barcode in the light. Now attend to the photon's polarization, the little arrow that marks the direction in which its electric field prefers to shake. As the photon slides through curved spacetime, that arrow is parallel transported. Gravity itself steers the polarization in a way that depends on the mass and the spin of the black hole. Around a rotating hole, frame dragging introduces an achromatic twist, a gravitational Faraday rotation that alters the plane of polarization purely through geometry, with no need for plasma. It is the gravitational cousin of the well-known Faraday rotation in magnetized gas, and it leaves a clean, frequency-independent fingerprint on the photon's orientation when the journey is done. Of course, the real environment is not empty. The photon is born in plasma, and along its way, the magnetized gas can also twist its polarization through ordinary Faraday rotation that grows with the square of the observing wavelength. In Sagittarius A star, careful modeling of polarized light curves and images indicates that a substantial fraction of this Faraday action may occur internally, close to the hole, which makes the polarized signal both precious and delicate. Separate the achromatic gravitational twist from the chromatic plasma twist, and you hold a stereogram of the near-horizon world. Geometry in one eye, magnetism in the other. This is why the year 2024 polarized image of Sagittarius A star felt momentous. By mapping the orientation of polarization around the ring, the Event Horizon Telescope revealed a field that is coherent, not chaotic threads of magnetism wrapped around the silhouette in an ordered spiral. That order is exactly what one expects when strong, organized magnetic fields accumulate near the brink, as in a magnetically arrested disk, shaping how matter drifts inward and how energy can be drawn from the spin. It is also the regime in which the subtle gravitational rotation of polarization can stand out against the plasma's own twisting, because the underlying pattern is not being shredded by turbulence. The image is a map of memory at the edge. Our lone photon, after skimming the brink, finally heads for Earth. On its way, it carries 3 souvenirs. The first is its delay, how long it lingered near the ring before escape, a measure that encodes how many times it looped, and thus where in the family of subrings it belongs. The second is its direction, the apparent position on the critical curve where it departed, which traces the silhouette's size and shape and therefore the mass and spin. The third is its polarization angle, a final orientation that records both the geometry's achromatic twist and the plasma's chromatic rotation along the path. When many such photons are collected by a very long baseline interferometer, these souvenirs combine into a set of interferometric signatures. The universal patterns that theory has shown are the unmistakable fingerprints of the photon ring. If we stand back from the mathematics, we can say it more simply. The ring behaves like a surface because it organizes what light can do. It sorts trajectories into families, those that plunge and those that skim, and it imprints delays and orientations that act like tags. It is an edge that remembers by constraining, an accounting line that writes without ink. In polarized images, that writing appears as graceful, rotating strokes. In interferometric data, as periodicities and phases. In time, as echoes that grow more widely spaced the longer the photon dallies near the brink. Each of these is a way an absent surface behaves like a present one. There is a further tenderness here that I love. The ring's memory is not brittle. It can change, and the changes themselves are a story. The magnetic field geometry around an accreting black hole is not fixed. It can wobble, reverse, and rethread, as plasma moves and reconnects. Observations of the black hole in Messier 87 across several years show that the polarized structure can evolve markedly, while the total intensity ring remains remarkably steady. A reminder that gravity provides the stage while magnetism choreographs the dance upon it. To watch polarization shift while the silhouette endures is to see the difference between geometry and weather. So our photon reaches us, bearing its small report from the edge. From many such reports, we assemble an atlas, a critical curve drawn to a fine line, a nested set of subrings whose spacing speaks of mass and spin, a polarization map whose swirls tell of coherent fields, and a chromatic twist that reveals the plasma's temperament. And over all of it, the knowledge that the achromatic rotation gravity's own hand has guided the tiny arrow on each wave. It is a quiet way for a horizon to tell us what it is made of. Not atoms, but constraints. Not molecules, but symmetries. Not stuff, but the rules that all photons must obey as they skim the ring that remembers. In the next step, I want to change my vantage point. Instead of riding with the light, let us stand at infinity with a very long baseline array and listen for the periodic fingerprints of those subrings, the interferometric harmonics that theory predicts. If we can hear those tones cleanly, we do not merely see the edge, we measure its properties with a precision that begins to feel like touching. All right, let us stand very far away with an Earth-sized ear and listen for the ring's harmonics. The way a very long baseline array hears an image is through a quiet piece of mathematics. Every pair of telescopes measures one ripple of the sky's Fourier song. A circle on the sky has a distinctive melody in that space, a sequence of oscillations that rise and fall with baseline length. A narrow ring sharpens the tune. Its Fourier transform becomes a nearly periodic pattern, with crests and troughs spaced by the inverse of the ring's diameter. Add a family of even narrower subrings, the photons that loop once, twice, and more times before escape, and you do not smear the music, you enrich it. On the very longest baselines, those subrings imprint universal oscillations that do not care about the messy details of the glow. They care only about gravity's geometry. That is why theorists say the photon ring writes a barcode into interferometric data, a code we can, in principle, read to weigh the whole, to feel its spin, and to test the theory of gravity itself with only a sparse array. There is poetry in the practice too. Earth turns. As it does, the distance and orientation between each pair of dishes sweep elegant arcs through the Fourier plane, as if we were dragging a comb across the song. Each new orientation samples another note. Together they sketch the whole melody. When the underlying picture is a luminous ring edged by a dark silhouette, the visibility amplitudes rise and fall with a rhythm set by the ring's diameter, while the phases, especially the closure phases that cancel instrumental mischief, lock onto asymmetries created by spin and by the little lopsided brightness of the flow. If we can catch several crests and troughs cleanly, we have something like a caliper made of starlight. The edge that is not a surface becomes, for a moment, a measurable rim. Now fold polarization into that listening. Polarization is a compass, and the Event Horizon Telescope's polarized view of the black hole at our galaxy's center tells us that the near-horizon magnetic field is not chaos, but choreography. Filaments of ordered field wrapped around the silhouette. A large polarized fraction means coherence below the instrument's blur. A spiral of preferred angles means the plasma's motion is guided, not shredded. That order is precisely what allows the subtle, achromatic twist from gravity, the parallel transport of the polarization vector in curved space-time, to stand out once we correct for the chromatic twisting caused by magnetized plasma. In other words, geometry whispers in one ear while magnetism speaks in the other, and with careful modeling we can tell the two voices apart. The physical picture that fits such order has a memorable name: the magnetically arrested disk. In this state, magnetic pressure grows so strong near the hole that it bottlenecks the inflow, piles flux up at the brink, and organizes the plasma into ordered lanes. Simulations and analytic work show that such a state naturally favors the extraction of rotational energy and can lay the groundwork for jets, even if a jet is faint or hidden in our particular object. The observational clue, coherent polarization wrapped about the ring, aligns with that narrative. It is the kind of consonance between data and theory that makes one trust the sketch long before the painting is complete. There is a little-known elegance in how energy can be drawn from a spinning hole under these conditions. In the Blanford-Znajek story, magnetic field lines that thread the horizon act like wires in a circuit, and the horizon behaves like a resistive sheet. The membrane paradigm gives this metaphor crisp numbers. The stretched horizon has a specific surface resistivity equal to the impedance of empty space. And when the load presented by the distant universe matches that internal resistance, power transmission from spin to electromagnetic energy is optimized. It is the engineer's language applied to curved space-time, impedance matching, power flow, Poynting flux, and although the sheet is a mathematical device, it yields the right astrophysics-energized fields, torques, and the possibility of collimated outflows. The edge acts like a terminal in a cosmic generator. Return to the interferometric fingerprints. The promise of the photon ring barcode is that it is universal. On sufficiently long baselines, where the narrow subrings dominate the signal, the oscillations depend only on a few global properties. That universality is forgiving. Even if the glow flickers, even if small-scale weather in the accretion flow rearranges hotspots from hour to hour, the long baseline fringes keep time with the ring. It is like listening for the bell tone beneath a choir, the timbre that never quite vanishes. Several teams have shown that by targeting those baselines and by tracking the periodicity as Earth turns, one can extract precise measurements of mass and spin, and with patience, begin to confront subtle predictions of the theory of gravity. What then of the future? The array that gave us the first images is already growing in ambition. Additional dishes, wider bandwidth, higher observing frequencies, and the prospect of new sights promise sharper ears and steadier hands. Plans for the coming decade speak of true movies, of our galactic black hole, of revealing a hidden jet if one exists, and of tracing similar polarized structures in other objects. Each improvement tightens the ruler with which we measure the ring and clarifies the script written in polarization. The edge will not merely be seen, it will be watched as it changes, teaching us how gravity provides the stage while magnetism writes the dance. It is worth pausing on a subtle gift the polarized images already give. When observers compared the organized fields around our galactic black hole with those around the giant in the galaxy of Messier 87, the resemblance was striking. Two very different environments, two very different mass scales, and yet the same spiral order at the brink. That rhyme suggests we are not looking at an accident of circumstance, but at a feature of horizons themselves. Wherever plasma threads a deep gravitational well, coherent fields can gather at the edge and shape the flow. Even news reports caught the poetry of that parallel order at the brink here and order at the brink there, hinting that the ring's material is not matter, but the rules that matter must obey. There is, finally, a practical lesson for the interferometrist's craft. Because the barcode is written in the Fourier plane, one does not need to make a perfect picture to measure the ring. One can design observing campaigns that prioritize the very longest baselines, schedule them to catch multiple oscillation cycles as Earth rotates, and combine the polarized visibilities in ways that emphasize geometry over weather. Closure quantities, closure phases, and closure amplitudes are allies here because they survive the day's small instrumental sins. In that sense, the photon ring offers a kindness. It gives us a target that is both delicate in appearance and robust in imprint. The edge behaves like a surface not only in the physics it hosts, but in the reliability of the mark it leaves on our instruments. So we have learned a quiet technique for touching what cannot be touched. We let the earth turn. We listen for the ring's harmonics. We let polarization tell us where the fields are taut and where geometry has twisted the tiny arrows on each wave. We borrow an engineer's language, impedances and loads to describe how a whole spin feeds the fields that thread its brink. And out of those simple, patient acts comes a portrait of substance without stuff, a knot surface that conducts, resists, rings, stores and remembers. The ring that remembers is made of constraints. It is made of symmetries. It is made of the laws that every photon must obey as it skims the edge and escapes to us with a story in its phase, its delay, and its polarized light. If you will indulge one more shift of vantage, I would like next to walk along the horizon itself, not as a traveler, which no one can be, but as a physicist translating geometry into the language of a boundary fluid. We will write down, in words not symbols, how expansion and shear become conservation laws on the edge, and how those laws make the horizon feel unmistakably like a living surface. Let us keep our promise and walk along the horizon, not as trespassers, because no one may cross from outside to inside and return, but as careful translators. Imagine the horizon as a luminous ledger drawn across space-time, and imagine that on this ledger, the universe writes in the language of flows. There are two simple words in that language: expansion and shear. Expansion is the rate at which a tiny ring of light on the horizon grows or shrinks as time passes for an outside observer. Shear is how that tiny ring is stretched into an ellipse, its shape changing even if its area momentarily does not. If gravity is strong and matter is pressing in, expansion is driven downward. The ring of light tries to shrink, and shear grows as tidal forces pull the ring out of round. These are not mere metaphors. They are the bookkeeping entries of the edge. Now translate those entries into conservation laws. The horizon, treated as a paper-thin surface, hovering just outside the true boundary, the stretched horizon obeys equations that are cousins of the familiar fluid equations. There is a law that looks like the conservation of mass, though here it counts energy crossing the surface. There is a law that looks like the conservation of momentum, in which the shear of the surface fluid and the pressure on the film determine how the horizon accelerates in response to stresses outside. If you once studied the equations that describe the flow of air over a wing, you would recognize the pattern, a balance of pressure, viscosity, and external forcing. But here the air is an effective two-dimensional fluid, and the forcing is the stress energy of whatever falls toward the whole. There is a beautiful sentence hidden in those balances. When light and matter fall in, they do work on the horizon. That work appears as heating of the surface fluid and as growth of area. The horizon's area is not a casual geometric detail. It is the measure of its entropy. So when I say that the area grows under the press of infalling matter, I am saying that the entropy increases exactly as a second law of thermodynamics would demand. In the membrane picture, you can even separate the growth into two parts. Entropy imported, because stuff fell in, and entropy produced, because the surface fluid itself dissipated energy through its finite electrical resistance and its finite shear viscosity. In ordinary life, a resistor turns electrical work into heat. A viscous film turns shear into heat. The horizon does both in its peculiar, universal way. Listen again to the fluid analogy. The surface has a temperature set by the strength of gravity at the edge, the surface gravity. The surface has a pressure related to that same quantity. The surface carries a shear viscosity and a bulk viscosity, that together determine how quickly disturbances smooth out. You can perturb the horizon, shake it with a passing mass, or tug it with a changing magnetic field, and it responds like a hot, thin, conducting sheet. It rings down with discrete tones until equilibrium returns, and its area increases by a small definite amount that records the dissipated energy. A surface is what it does, we said earlier. The horizon does the work of a surface perfectly. Electromagnetism joins the story with equal elegance. Maxwell's equations, written in the presence of a boundary, insist on specific relationships between fields and the charges and currents living on that boundary. When we replace the true horizon with a stretched, time-like film, we are obliged to populate the film with a surface charge density and a surface current that make those relationships come true. If a magnetic loop sweeps across the edge, a current flows on the skin. If a charged particle approaches, the surface charge rearranges to maintain the proper field lines. The numbers that emerge are universal. The sheet behaves as if it had a fixed electrical resistivity set by the properties of empty space, and the rate at which it turns electromagnetic work into heat follows the same simple rules that an engineer would write down for a metal foil. In that heat is the area. Increase in that area increases entropy, and in that entropy is the quiet assertion that the ring remembers the passage of the field. Because the edge speaks the dialect of fluids, it is natural to ask whether there is a wind along the horizon, a drift, a circulation. In stationary situations, the answer is serene. The flow vanishes in the right frame, and the surface simply carries tensions and pressures without sliding past itself. But the moment you feed the hole, drop a star across the brink, or let magnetic flux pile up the horizon, supports lateral stresses and transient flows that look, in the equations, very much like weather. The shear of the surface fluid grows, the effective pressure increases in patches, eddies appear and are damped away by the universal pressure, viscosity. That damping is not decorative. It is the mechanism by which the horizon converts organized motion into heat and therefore increases its area. You can think of it as a tide on a shoreline that never recedes, only creeps a little farther up the beach each time a wave arrives. There is still deeper structure when we zoom in, almost absurdly close. At the edge, the natural speed for motion along the surface tends to zero, and a special symmetry, the Carolean symmetry, takes over. In that limit, the conservation laws of the boundary fluid become even sharper. The expansion becomes a statement about how the clock of the edge ticks. The shear becomes a statement about how momentum is transported when local motion along the surface is heavily constrained. It is a peculiar fluid, to be sure, one that carries stress without conventional motion, but it is a fluid all the same, and its equations are the horizon's way of remembering what presses on it from outside. Everything I have said so far lives on the gravitational side of the ledger, but it rhymes with what quantum theory tells us about information. Boundaries host edge modes, subtle degrees of freedom that record how fields thread the surface. On an ordinary tabletop, you may ignore them. On a horizon, you may not. They appear in the entropy you compute for the region outside. They appear in the careful derivations that recover a sensible, unitary account of evaporation when quantum extremal surfaces and islands are taken into account. In every register, we can tune thermodynamic, electromagnetic, hydrodynamic, quantum. The rules point in the same direction. The edge keeps the books. I like to hold all of this in one image. Picture a drum skin stretched across a black circle. The skin is not made of atoms, it is woven from rules. Tap it with a falling star, and it rings in a set of tones that depend only on the mass and spin of the whole. Draw a magnet across it, and currents run, doing work and warming the skin. Drag a rivulet of plasma along its face, and shear grows, only to be smoothed by the skin's universal viscosity. Each tap, each draw, each drag leaves a tally, a tiny increase of area, a tiny raise in entropy, a tiny change in the alignment of the near-horizon fields that shows up billions of years later in the polarization of light reaching our telescopes. That is what I mean when I say the ring remembers. The ledger is written not in ink, but in consequence. From this vantage, the familiar laws of black hole mechanics are not esoteric proclamations. They are the everyday habits of a surface. There is a law that says the strength of gravity at the edge plays the role of temperature. There is a law that says the area behaves like entropy. There is a law that says when you do work on the hole, spin it up, feed it the edge, updates its energy, its temperature, and its area in a tightly coupled way. And there is a law that says so long as reasonable energy conditions hold, the total area never decreases. Each one reads, to me, like a sentence from a handbook about materials, how a particular film responds when stressed, warmed, or stirred. The horizon is that film, and the cosmos has been testing it since the first stars died. In our next step, I want to put these laws to work in a concrete story. Let us drop a small magnetized star past the brink of a rotating hole and trace in plain language how the edge's fluid equations, its electromagnetic boundary conditions, and its thermodynamic bookkeeping conspire to record the event exactly how the ring remembers the fall. Let's drop something modest but evocative. A small, magnetized star past the brink of a rotating black hole, and watch how the edge keeps the books. I picture it as a compact ember with its own magnetic field, a tidy bundle of flux lines wrapped around a luminous core. As it falls, space-time's rotation begins to grip the field, dragging the footpoints into a slow twist. At the very last moment, when the star brushes the region just outside the true boundary, the membrane description becomes indispensable. We replace the horizon with a paper-thin, time-like stretched surface, and we are instructed by long practice, not whim, to endow that surface with electrical conductivity, shear viscosity, and temperature. In that picture, the approaching magnetic loops induce surface currents on the skin. Those currents are not decoration. They are the precise boundary data needed to satisfy Maxwell's equations outside, while nothing escapes from within. There is a memorable number attached to this story. The stretched horizon behaves like a resistive sheet, whose surface resistivity equals the impedance of empty space, about 377 ohms. When our star's field lines sweep across the edge, a surface current flows proportional to the tangential electric field. Ohm's law holds on the skin. Electromagnetic work done on that sheet is converted into heat in the fictitious film and, in the exact accounting of black hole mechanics, into an increase of the horizon's area, its entropy. It sounds like engineering language in an exotic setting, but it is the right language. A resistive sheet, pointing flux into the surface, and a ledger that grows by a definite amount when work is done on it. Now watch how rotation turns boundary bookkeeping into power flow. Around a spinning hole, magnetic field lines that touch the horizon can behave like wires in a dynamo. As the falling star's flux is dragged and anchored on the membrane, the system resembles the classic Blandford's-Najac circuit. The horizon acts as a resistive element in series with the distant load. And when the impedance of the external universe matches the sheet's characteristic resistance, energy extraction is optimized. In that regime, part of the hole's rotational energy is handed to the field and carried away as electromagnetic power, pointing, flux that can, in other circumstances, collimate into jets. It is a satisfying synthesis. The membrane gives the numbers, the circuit picture gives the intuition, the general relativistic magnetospheres and simulations show it happening in detail. What becomes of the star's own magnetism as it crosses the brink? The surface currents rearrange to preserve the field's constraints. Magnetic flux does not simply end, and the membrane's charges and currents adjust so that the external fields remain regular at the horizon. In the language of force-free electrodynamics, there is a regularity condition at the edge, the Znayak condition, that fixes how field lines cross the horizon without singular behavior. For an outside observer, that condition and the membrane currents together ensure a smooth handover. The information about how the field was threaded is transferred to the boundary variables that we are allowed to see. The ring remembers by maintaining the correct pattern of currents and potentials, even as the star itself slips beyond return. All the while, the gravitational bookkeeping proceeds with its own clarity. The laws of black hole mechanics say that when you do work on the hole, by dropping in energy, by delivering angular momentum with the twisting field, the horizon responds with linked changes of mass, spin, and area. In precise form, the first law relates the change in mass to surface gravity times the change in area, plus the horizon angular velocity times the change in angular momentum, plus an electromagnetic term if charge is involved. For our falling magnetized visitor, these terms translate into an orderly statement. Energy and angular momentum fluxes across the edge are balanced by growth of area and a change in the hole's spin. Nothing mystical, just a ledger that never loses a page. There is a stern guarantee behind that ledger. The area cannot go down in classical physics. Hawking's area theorem tells us that, under reasonable energy conditions, the total horizon area of black holes never decreases. So when the star's field does work on the membrane and when the star's rest mass and any remaining kinetic energy cross the edge, the film must swell. The increase may be minuscule for a small starlet and a supermassive hole, but it is definite, and it is the gravitational analog of frictional heating and viscous dissipation in an ordinary material surface. Observations of black hole mergers have even begun to confirm this principle empirically. The remnant's area exceeds the sum of the progenitors, just as the theorem demands. The magnetic choreography near the brink has its own preferred states, and they help us interpret real images. When enough flux is delivered toward the hole by a falling star, or by steady accretion, the inflow can become magnetically arrested. Magnetic pressure piles up at the edge, throttling the gas and organizing the flow into ordered lanes. This mad state is particularly efficient at tapping rotational energy and producing pointing flux outflows in simulations. The polarized image of Sagittarius A star in the year 2024, showing a coherent spiral of polarization angles wrapped around the silhouette, fits naturally with such organized fields at the brink. It is exactly the kind of near-horizon order the membrane and circuit picture anticipates. If we were to listen to the edge as the star crosses, we would hear it ring. The sudden perturbation excites the black hole's quasi-normal modes, the damped tones by which the horizon relaxes to equilibrium. In the membrane language, those notes are the collective oscillations of a hot, viscoelastic sheet. In the gravitational wave language, they are universal spectral lines set only by mass and spin. Either way, the message is the same. A surface is what it does, and the horizon's way of doing is to ring, to dissipate, and to grow. Even the photon story plays along. As the star's field twists the near-edge environment, photons born just above the horizon skim the ring and carry away little souvenirs. Delays from extra loops, positions on the critical curve, and polarization angles that include an achromatic gravitational twist from parallel transport in curved spacetime and any chromatic Faraday rotation in the magnetized gas. With enough such photons, an interferometer recovers the ring's harmonics, a barcode of crests and troughs in the Fourier plane that depends on the geometry more than the messy details. The edge not only remembers, it leaves a clean imprint on our instruments. So the fall of a small, magnetized star is written twice, once in gravity's ledger, where energy and angular momentum flows raise the area according to the first law, and once in electromagnetism's ledger, where horizon currents, with their characteristic 377 ohm sheet, absorb and redirect the field's work into heat, and if the circuit is matched, into outward pointing flux. That is what I mean when I say the ring behaves like a surface. It conducts, it resists, it rings, it warms, and, above all, it remembers. If you will stay with me a little longer, I would like next to turn from a single infall to slow weather, how the edge keeps time over months and years as flux accumulates and reverses, and how polarized images can catch those gentle mood changes while the silhouette, the geometry itself, remains serenely the same.